Hello everyone. We will again discuss some problems related to the concepts that we already have studied. So, we already have studied Fermi-Dirac statistics, Fermi energy level, what are the different positions of Fermi energy level in the band diagram, energy band diagram. We also have seen how Fermi energy level, the position of Fermi energy level can be changed if the semiconductor is extrinsic, or we will see some more details about this in the coming lectures. We sort of studied some of the carrier concentration related considerations, how intrinsic carrier concentrations are measured. We studied what is NC, what is NV. We studied what is NA, what is ND, that is donor and acceptor ion concentration, how they are related, and associated concepts. So, today again we will solve some problems related to Fermi level and diffusion and mobility, and we'll try to see that how we can approach to a problem once we have some given conditions, and then how to get the required results or values from that given problem. I mentioned in the last problem solving exercise also that please don't take this as a problem solving exercise only, rather we can also take it as a real life problem solving considerations. For example, when we design some sensor or when we design some electronic devices, how do we actually calculate different values based on the situation, practical situation, and then can come up with a solution and novel sensor design and novel device concept and novel sensor concept, so on and so forth. So, today again we will start with different questions and we will see how to approach that particular problem to solve it. So, the first question is, calculate the thermal equilibrium concentration of electrons and holes for a given Fermi energy. Consider silicon at T equal to 300 Kelvin, so that Nc is equal to 2.8 into 10 to the power 19 and Nv is equal to 1.04 into 10 to the power 19 per centimeter cube. Assume that the Fermi energy is 0.25 electron volt below the conduction band. If we assume that the band gap energy of silicon is 1.12 electron volt, then the Fermi energy will be 0.87 electron volt above the valence band. So, if you look at this problem, I think we already have solved something similar in the previous question or in the previous lecture related to problem solving. So, now even in this question we have different values given, and if you look at the question, there are so many values, at times you may get confused how to approach the problem and how to start the problem. The best thing that we should do in the beginning is to write down the values that are given. So, the temperature T is given to be 300 Kelvin. So, this part is clear. And second thing is, at T equal to 300 Kelvin, the value of Nc is also given, which is 2.8 into 10 to the power 19 per centimeter cube. The value of Nv is also given, which is 1.04 into 10 to the power 19 per centimeter cube, and the Fermi energy is given as 0.25 electron volt below the conduction band, meaning I already have explained this. So, your Fermi energy level is EF is EC minus 0.25 electron volt, and then the value of Eg is also given, which is 1.12 electron volt, And then if this is the case, then your Fermi energy also can be given as 0.87 electron volt above the valence band, meaning your Fermi energy can also be given as EV plus 0.87 electron volt, right. So, if you look at this, you can understand that both EC minus EF and EV minus EF minus EV, both the values are given. From here you will get EC minus EF, from here you will get EF minus EV. And if you draw the band diagram, say this is your EV, this is your EC, and this is where your EF is, you can understand that your Fermi level is 0.25 electron volt below the EF, which is this 0.25 EV, and 0.87 electron volt above EF, above EV. So, this is 0.87 electron volt. So, from here also you can calculate what should be your energy band gap, because see, according to this calculation, both of these should add up to your EG, that is your 0.25 and 0.87. If you look at both of these values, then and if you add them 0.25 plus 0.87, then it gives you 1.12, which is your EG. So, all these informations are in agreement with each other. So, you already have these information in the question. Now, what you need to calculate? You need to calculate the thermal equilibrium concentrations of electrons and holes. So, you need to calculate N0 and P0. So, this is what we need to calculate, and we already know the value of N0 can be calculated by NC exponential minus EC minus EF divided by KT is something that we use for calculating N0. Similarly, for P0 it is NV exponential minus EV minus EF minus EV divided by KT. So, these are the two equations that we use. Now, the value of NC is given here. The value of EC minus EF you will get from here. So, EC minus EF will be 0.25. The value of KT is 0.0259 electron volt at T equal to 300 Kelvin. So, if you are T equal to 300 Kelvin, the value of KT is 0.0259. So, please memorize this number, because this is very important, and in many cases you will find that you need this value. And then if you put all these values in this equation, the value of N0 that you will get is 1.8 into 10 to the power 15 per centimeter cube. Similarly, the value of P0 will be 2.7 into 10 to the power 4 per centimeter cube. So, this is the value of N0, this is the value of P0. So, from here itself it is very clear the concentration of electrons, the equilibrium concentration of electrons is much higher than the equilibrium concentration of hole. So, this is an N-type semiconductor, right, because this concentration is higher, electron is higher in the material compared to holes. So, this is majority carriers, and that is why you see that the value of EF is not right in the middle. So, it is close to EC because it is only 0.25 electron volt below EC and 0.87 electron volt above. So, it is close to EC. So, from this information you get this details about this particular semiconductor, and this is just in problem solving as of now that we have just explained, but in real life also you may need to calculate these values based on the requirements. So, you can approach to a real life problem also similarly, because these informations are kind of real life situations. So, for example, now once you have all these details, if one asks you what could be the value of N0 and P0 if your temperature is increased by say 50 degrees centigrade, then you need to calculate the value of T in terms of Kelvin, what is that value, and then at that particular temperature you have to calculate the value of N0 and P0. So, similarly, this problem can be extended to different other problems, and at the first instance when you see the problem you may find that this is very complicated, but if you approach it systematically you will get to know that the problem is not that difficult, it is just the approach that you have taken probably makes the problem more complicated. Okay. So, let us go to our next problem. The next problem is determine the required donor impurity concentration to obtain a specified Fermi energy. So, the silicon at 300 Kelvin contains an acceptor impurity concentration Na to be 10 to the power 16 per centimeter cube. Determine the concentration of donor impurity atoms that must be added so that the silicon is N-type and the Fermi energy is 0.2 electron volt below the conduction band edge. Okay. So, in this case also if you look at this problem, we have multiple information given. The first information is T is equal to 300 Kelvin, temperature is already defined, the value of Na is 10 to the power 16 per centimeter cube. Then the next is determine the concentration of donor impurity atom that must be added so that the silicon is N-type and the Fermi energy is 0.2 electron volt below conduction band. So, EF, this is the requirement, EF should be EC minus 0.2 electron volt, right. Now, we already know the equations like Nd minus Na, let me write it here, Nd minus Na is equal to Nc exponential Ec minus Ef divided by Kt. So, there is a minus sign also, right. Now, previously also we have written similar expression. If you look at here, Nc is equal to Ec minus within bracket Ec minus Ef divided by Kt exponential, right. That is the value of your equilibrium concentration of electron. Now, let us go there. This is basically the equilibrium concentration of electron. Now, in this case you look at this, because this particular semiconductor or the silicon block has to be N-type. So, your donor atoms should be higher, the concentration of donor ions has to be higher compared to the acceptor ion. Now, the value of acceptor ion is already given. So, the concentration of your electron is basically the difference between the donor atom minus the concentration of the donor atoms and minus the concentration of the acceptor atoms. So this is what exactly we have written. So the same equation is written in a different way, and now if you put the values, and what you need to determine? You need to determine the concentration of donor impurity, that is ND. What is ND? That is what we need to determine. So it's very clear now, the ND is equal to Na plus Nc exponential minus Ec minus Ef divided by Kt. So the value of ND I think is already given. The value of Na is already given. So Na is equal to 10 to the power 16 per centimeter cube. So your value is 10 to the power 16 plus the value of Nc is also given. The value of Nc is equal to 2.8 into 10 to the power 19, which is already given. But if you look at this question, this value of Nc is missing. So basically the value of Nc should be given, and probably this question is a follow-up question to this, where the value of Nc is already there. So this both the question are related, and that's why I have taken the value of Nc from the previous question. See, if this value is not given in this question, then we can't solve this. We need this value of Nc. So considering question 1 and question 2 both are related, I have taken the value of Nc from the previous question, and then we have exponential minus Ec minus Ef is 0.2, and the value of Kt at T equal to 300 Kelvin is 0.0259 electron volt. Right. Now, if this is the case, then the value of Nd will be 10 to the power 16 plus 1.24 into 10 to the power 16 per centimeter cube. Now, this is basically 2.24 into 10 to the power 16 per centimeter cube. Now, one thing that is very clear in this case is our Nc value was not given. So, the value of Nc is important in this question, and to solve this problem I have taken the value of Nc from the previous question, because I have considered both the equations are related. This is just an assumption that I have taken. The value is not given here, meaning we can't solve this standalone. So, we need that value in some way or other. So, this is how we can solve this particular problem, and if any details is missing, you can once check whether this details is something which is very obvious. For example, the value of Kt is also not given, but value of Kt at T equal to 300 Kelvin is something that is well known. So, you can't just write that the value of Kt is missing, because K is an Boltzmann constant and we know the value, it's a constant. So, we know the value, we should know the value basically. In most of the cases, people provide the value of K. T is temperature, temperature is already given. So, value of Kt basically is the multiplication of Boltzmann constant with the temperature, which at T equal to 300 Kelvin comes out to be 0.0259. And it's better that we remember this value, because remembering Boltzmann constant is not an easy task, because Boltzmann constant can be of different units. So, in this case the unit that we should remember is electron volt per Kelvin. That is the unit that we should consider when we are solving these problems. Unit of Boltzmann constant that we should consider. This could be Joule per electron Joule per Kelvin also. So, there are different units also. So, it's difficult to memorize the Boltzmann constant. So, it's easier to memorize 0.0259 or sometimes 0.026. 259 is approximated at 0.026 electron volt. But nevertheless, in this case the value of NC is needed, and that way we can actually solve the problem. So, let us go to the next problem, which is related to diffusion, and the question says calculate the diffusion current density given in a density gradient. So, our purpose is, or what we need in this case is to calculate the diffusion current density, and the assumption that is given over here is, assume that in an n-type gallium arsenide semiconductor at T equal to 300 Kelvin, the electron concentration varies linearly from 1 into 10 to the power 18 to 7 into 10 to the power 17 per centimeter cube over a distance of 0.1 centimeter. Calculate the diffusion current density if the electron diffusion coefficient is 225 centimeter square per second. So, this is what the information that we have. So, again the first step is to write down the values. So, the temperature is 300 Kelvin, and nowhere in the question it is said that the temperature has been varied. So, T is equal to 300 Kelvin. Then we have electron concentration which is varying over a distance. So, electron concentration we can write N1. So, let us write here only. So, electron concentration N1 is 1 into 10 to the power 18 per centimeter cube, and this is for x is equal to 0, when distance is equal to 0. The concentration of electron is 7 into 10 to the power 17 per centimeter cube when your x is equal to 0.1 centimeter, right. So, with distance it is changing, and the delta x, meaning the change in distance, is 0.1 centimeter, right. This is how the distance is defined in the question. Then we have electron diffusion coefficient, which is Dn, as 225 centimeter square per second, given over here, right. Now, in this situation, let us calculate the concentration gradient. The electron concentration varies linearly, so we can consider that dn dx is equal to n2 minus n1 divided by delta x, because it is changing linearly. So, n2 minus n1 divided by delta x is basically your dn dx, and the diffusion current density Jn diffusion, the equation is q dn into dn dx. Now, in this case, q is nothing but the charge of electron, which is 1.6 into 10 to the power 19 coulomb, and the value of dn is already provided. So, it is 1.6 into 10 to the power 19, dn is given here 225. Now, dn dx is nothing but n2 minus n1, that is this 7 into 10 to the power 17 minus 1 into 10 to the power 18 divided by 0.1. So, in this case, basically it has to be mod value, because we are actually looking at delta n, the change in concentration, but in this case the NTU that I have written is smaller than n1. So, it is basically 1 into 10 to the power 18 minus, so it will be 1 into 10 to the power 18 minus 7 into 10 to the power 17, and if you do this calculation, you will get a value which is 108 ampere per centimeter square. So, this is what the diffusion current density in this particular problem. So, in this case, first we have these values, and then because it is already said that the concentration varies linearly, so your dn dx value is this, and the equation for diffusion current we already have seen in the lectures, that the value of diffusion current is q dn dn dx, and we just put the value, and ultimately we get the current density value from this problem. So, this is a problem related to diffusion current, where all the details are given, and then you have to approach this problem in this way. So, we also have another problem which is similar, where it is said that determine the diffusion coefficient given the carrier mobility. Assume that the mobility of particular carrier is 1000 centimeter square per volt second at t equal to 300 Kelvin, right. Now, in this case also you have the mobility value which is mu 1000, and then temperature 300 Kelvin, and we know that D is equal to mu into Vt, where Vt is thermal voltage. So, Vt is equal to Kt by Q. K is Boltzmann constant, and we know T is 300 Kelvin, and Q is nothing but 1.6 into 10 to the power 19 coulomb, 10 to the power minus 19 coulomb. So, the value of Vt, if you put all these value, say the value of K is 1.38 into 10 to the power minus 23 joule per Kelvin. Now, please note here the value of K is written in the unit of joule per Kelvin, but previously we once wrote this value of Boltzmann constant in one of the problem solving lectures, where we have considered electron volt per Kelvin. So, the values are different. So, the value you have seen there is different from the value that we have here. Now, you have the value of K, you have the value of T, and you have the value of Q. Put all these values in this equation, and then you will get a value of Vt which is 0.0258, which is this much volt, which is close to 26 millivolt. So, please also note at T equal to 300 Kelvin, the thermal voltage is close to 26 millivolt. We know the value of Kt at 300 Kelvin in electron volts, we have already seen, but the value of thermal voltage at T equal to 300 Kelvin, the value is close to 26 millivolt. In some cases, people also use 25.9 millivolt because it is 0.0258 something. So, it is 25.9, but we can approximate it as 26 millivolt as well, right. Now, if you calculate the value of D, which is mu into Vt, the mu is already given 1000, and the value of Vt is 26, say 26. So, it will be almost 26 into, so okay, this is, please note, this is centimeter square plus volts second, and this is volt, which is coming out to be 26 centimeter square per second. So, this is what the value you will get when you calculate the value of D here. So, one thing that you should note here, the value I have written here is in millivolt, and technically I should write this value as volt, which is 0.026, this one. and then if you multiply this with 1000, it will be around 26. So that is why I have written 26 centimeter square per second. So one thing that one should be very careful about is the units, and if the units are not correctly placed, you will definitely get a value which is wrong. So please check the units properly and see that the units are written correctly while you are doing the calculation. So in this case, because I have written it in millivolts, so somebody may think that it is 26,000. The result should be 26,000, but this is in millivolt. So we should convert this in volt, because this particular value is in centimeter square per volt second. So that is why we have converted this in volts and then calculated the value, which is around 26 centimeter square per second. So that is what the diffusion coefficient in this particular problem. So with this, we will conclude the lecture today, and we have seen problems related to mobility, problems related to diffusion coefficient, problems related to Fermi energy level, how to approach those problems. We will also solve few more problems as we progress and cover few more conceptual ideas. But for the time being, let us conclude. My request to all of you would be to practice some more problems at your home, and in the coming lectures we will study more concepts associated with semiconductor physics. Till then, thank you.